I would like to continue with the hypothesis tests. And once we talked about how the hypothesis tests are constructed and how, maybe not in detail, but as an overall view of how these hypothesis tests are carried on using sample statistics, I'd like to mention a very important point about these hypothesis tests, which we call type 1 and type 2 errors. Type 2 errors, type 1 errors are usually denoted with alpha, and type 2 errors are denoted with beta. Actually, in this course, we are going to be mainly concentrating on type 1 errors. But on the other hand, also I would like to give a general idea about type 2 errors. So what do I mean by type 1 and type 2 errors? All right. So let's go back to that hypothesis testing structure, I may say. The idea was, once we construct our hypothesis, we define an acceptance region and we define a critical region. Then we collect a sample of a certain specific size of n elements that we have specified. And then depending on where X bar falls, whether it falls in the acceptance regions or in the critical region, we, we reach a conclusion. So there are two types of possible wrong conclusions here. First of all, why can we reach a wrong conclusion? Because recall that our conclusions were like, if our X bar value were in a critical region, then we would say that, so it's here or here, then we would say that we reject the null hypothesis. And if it is in the acceptance region, we do not say we accept the null hypothesis, but we say that we do not reject the null hypothesis. Basically, it's the one of the ways of summarizing these two conclusions. On the other hand, note that these are probabilistic conclusions. What do I mean by that? Actually, I haven't shown you still how to construct this acceptance region, are actually these critical values, but these critical values will be based on a certain significance level. And significance level, if you recall, is actually equal to 1 minus significance level is confidence level. So when we say, for instance, a confidence level of 0.95, we are talking about a significance level of 0.05. But what I mean is, this confidence level cannot reach 1. If it reaches 1, then the critical values would be at minus and plus infinity, which would not mean anything. When you have finite critical values, these will correspond to a confidence level smaller than 1 and a significance level greater than 0. And in this case, for instance, the probability that, if we are talking about probability less than 1, it does not mean that this is always going to be true. What do I mean by that? It is going to be, our conclusion may be wrong. It may be, well, depending on this probability may be equal to 0.99 confidence level, which corresponds to a significance level of 0.05. But it still means that for 1% of the times we conduct the test and we apply this procedure, we are going to obtain a wrong conclusion. So what types of wrong conclusions can we have? Let's talk about this. All right, the first type of wrong conclusion is what we call type 1 error, which is actually shown with this alpha, type 1 error probability alpha is. And note that this is going to be equal to significance level, and there's no coincidence, we're going to see the relation. So X bar falls in the critical region. So the X bar value that we find from sample is going to be either here, for instance, it's going to be equal to 3.5. In this case, we would say that because it is the procedure of both the architecture, due to the architecture and the procedure of hypothesis testing and this current hypothesis, we reject the null hypothesis that mu is equal to 3.0. But we should realize that it is still possible that due to random sampling, we could have really obtained a sample mean value of 3.5 from a population which has a population mean value of 3.0 kilomoles, 3.0 kilomoles per meter cube. So from this population, right, it is possible that we could have obtained a sample with sample mean of 3.1 value. But on the other hand, therefore, it is actually the population mean is actually 3.0. That is, the null hypothesis is actually true. But we do not, of course, know that. But assume that the truth of that assumption or hypothesis is later told to you. But you apply this procedure and you find that since this is equal to 3.5, you say that you reject the null hypothesis in terms of the alternative one, which says that mu is not equal to 3.0. So you agree with this alternative hypothesis. On the other hand, indeed, this is equal to population mean is equal to 3.0, and this sample consisting of different elements and which gives a sample mean of 3.5 has actually been sampled from this population. This is called type 1 error. And this is basically, there is eraser, oops. Yeah, this is actually equal to, let's first concentrate on the right-hand side. It is given that H0 is true, it is the probability of rejecting H0. Now, what does that mean? If this is our distribution for X bar, let me use a different color pen, it's going to be better. Can I use in color? Yes. Let's see, yeah. So this is our distribution for X bar. And here, this point is going to be equal to mu, population mean value. And for this case, it's going to be equal to mu0. So we just continue on the condition that H0 is true. So H0 is true means that mu is equal to mu0. This condition entails this one, and mu is equal to mu0 means that expected value of X bar from this sample is going to be equal to mu0. Therefore, this is going to be the distribution of X bar. Note that in reality, we wouldn't be knowing this, but in order to analyze this whole thing, we just assume that we know that H0 is true. Now, in this case, what we do is to determine those critical regions here and here. So this is going to be a lower critical value, this is going to be an upper critical value. And what we do here is actually, I'm just showing the same thing here on a distribution. This part is going to be, this region is going to be our critical region, and this is going to be our acceptance region. And if the value, and let's say that this is equal to 3.4 and this is equal to 2.6. And if our X bar values come out to be equal to 3.5, we reject the null hypothesis. On the other hand, actually it is true. And as you can see, it's from this distribution. So the question is this: what is the probability of rejecting H0 while this distribution is valid? It actually means, if I get rid of values here, so let me also get this 2.6 and this one. Yes, it is anywhere in this region. You will see greater than 0 and LC's low value smaller than LC. Therefore, these two probabilities, the areas under this curve, if you sum these values, we are going to end up with this probability. Because it is this distribution is the distribution of H0 with a probability mean of mu0. And from this distribution, note that it is possible that we may have samples with sample mean which falls in these regions, lower than LC and upper than UC values. Therefore, we just find the probabilities here. And note that since this is symmetric distribution, the left-hand side is going to be equal to, if you take the whole area as area over 2, area over 2. And when you sum them, it's going to be all area. Now, what is this area equal to? This is going to be exactly equal to alpha value. And I'm going to show that, which is the significance level, but you can actually associate this with what we have covered previously in terms of confidence intervals. It's a very similar approach. Confidence interval for mu is going to be between a lower and upper limit, and that lower and upper limit, these tails, when you sum these tails, there were alpha over 2, and when you sum them, the remaining probability, I call this the probability being sacrificed equal to alpha. There is a very similar thing going on here. I will show you the exact relation later while solving the questions, but the tail areas will be simply equal to alpha. So significance level is what we call actually type 1 error, which means although the H0, the null hypothesis is true, we reject it. This is also, note that this is also called false positive, especially in people, in doctors, in health sciences related with health issues. False positive term is used. And these in nowadays, actually, the issue related with coronavirus is a very good example for that. Now, think about testing whether a patient has coronavirus or not case, right? So in this case, what they quite possibly, I don't know anything about what they do. Probably they actually take a sample from the nose or from the throat maybe, and they probably count the number of some microorganisms or things like that. Actually, I do not know. But what usually those tests generally do is they assume that, right, there is no, let's say, there is the patient is normal, I may say, right? Coronavirus is not there. So in this case, the normal patients have a certain, whatever they measure, that there is a certain distribution which is obtained from the whole population. So people without coronavirus have that distribution of that variable, whatever that variable is, in the whole population. So when it comes to, and let's say that, assume that people, when they have coronavirus, this curve shifts to this direction. So a high value of X leads to a diagnosis of coronavirus. So in this case, what people do is during these tests, they actually take an upper level here, limit here. And they say that if the X value taken from that patient, who is now not known, still known whether he or she has coronavirus or not, if the X value is greater than UC, upper critical value, then that person, let's forget about this coronavirus, because actually that is probably has got nothing to do with coronavirus, but the general the general structure of medical tests. If X is greater than UC, then test is positive. Now here is a problem. Note that since this is the distribution from normal people, right? Wherever you cut this line so that the higher values will correspond to people with the virus or people who are sick of that disease, this is going to also include some people without that sickness, which is this probability. So this is going to be exactly type 1 error. So why is this called false positive? Test is positive. On the other hand, actually that person has no disease. So probability that test is positive but no disease case is what we call false positive, which is also equal to type 1 error. And type 2 error is, we this time look from the different direction. This time H0 is not really true. So mu is not equal to mu0. On the other hand, the X bar value you find falls somewhere here. This is possible. Let's assume for the sake of this question, mu is equal to 3.2 kilomoles per meter cube. Here. This is going to have a distribution. So the sample that we are going to be obtaining may be anywhere. Okay, it may be anywhere here, a much higher value, but it may be a lower value. It may be around this value. And let's say that X bar has come out to be somewhere here. And due to sampling variability, it is very well possible. And when it's in acceptance region, we would not reject this mu is equal to 3 kilomole per meter cube. Although we say that we do not say that we accept that mu is equal to 3.0, we still do not reject the null hypothesis. Although in essence, mu is equal to 3.2, so null hypothesis is incorrect. Therefore, this is called false negative. And the way it is shown is this time, H0 is not true, but we do not reject H0. And this is shown with beta. And this is in health sciences, this is called a false negative. Why? Because this time the test result will be negative. On the other hand, the patient really has that disease. So that's a very, again, a very typical case related with coronavirus tests. So both of these errors are realized in both in any type of statistical tests and also any type of test related with health sciences. So one may look or summarize everything in that table. Now, this part, these rows correspond to the decisions that we make or the result of the test. On the other hand, these two columns correspond to the essential reality. So H0 may be true and we fail to reject H0. So really mu is equal to 3.0, right? And our X bar falls somewhere here. This is the case of no error. Similarly, H0 now is false, so mu is equal to some other value. Mu has increased to 4.0 kilomoles per meter cube. Of course, in reality, we wouldn't be knowing that, but as I said, this is just to understand what's going on. So this essence part. So in this case, X bar, let's say, falls somewhere here, and we reject the null hypothesis, and it is correct that we reject the null hypothesis, therefore it's going to be no error. This one, on the other hand, H0 is true, but we reject H0 erroneously, is type 1 error, which is actually a false positive. Actually, we rejecting, note that in tests, rejecting H0 is a positive. While in decisions, fail to rejecting H0 is negative. And the idea actually comes from when it comes to medical tests, H0 is no disease, H1 is disease. Therefore, a positive result means there is disease. And note that here this has the burden of proof. And H0 in this case means that the test was unable to determine that disease it was looking for. It does not mean that that person is healthy. It is very similar to, again, the status of null hypothesis, like in the jury system or in other issues. Now, the arithmetical part, how do we determine alpha value? So assume that X is normal and sigma is equal to 0.8 kilomoles per meter cube. And let's say that acceptance regions taken to be between 2.6 and 3.4. We take a sample of 16 observations. All right. So in this case, we first construct a hypothesis. And the hypothesis is, as we talked about, still talking about the same question, true or not true. This is the hypothesis. And mu0 is equal to 3.0. That's why actually mu is equal to b0 is the null hypothesis. So here is the point. If H0 is true, if null hypothesis is true, and that's how we always approach the problem, then X is going to be normal distributed, right? Because it's given in the question that X is normal. is going to have a population mean of mu0. Why? Because we assume that this is true, and it's going to have a population standard deviation of 0.8. Actually, I should have written sigma square. All right. So x bar is going to be again normal because it's a linear combination of x, and it's going to be mu0 because expected value of x bar is going to be expected value of x, and the variance is going to be population variance divided by n. Let's continue. Therefore, x bar is going to be normal distributed around 3, and the variance is given, right? Divided by 16. 16 is the number of samples, and actually that's x bar is the sample average of that 16 observations. And the result is given there, 3.0 and 0.2 to the power 2. Therefore, the distribution is going to be taken from MATLAB. The distribution of x bar is really going to look like this one, if the null hypothesis is true. All right. Now, as you can see, referring to the previous case, if you would like to commit no errors, then your critical values should be at minus and plus infinity. Since this normal distribution doesn't decay to 0 anywhere, at any finite value, if you draw the critical values, even if you denote the critical values, if you make the critical values equal to 2.2 and 3.8, note that since these do not decay 0 here, there is still non-zero probability on this tail and on this tail. So there is always going to be a type 1 error, unless you take this lower limit to minus infinity and plus this one to plus infinity. In this case, there is not going to be any type 1 error. While you may think that we solved the problem, unfortunately, in this case, we increase the type 2 error to 1, by the way. Type 2 error probability. All right. So now the next thing that we do is we determine a lower critical value, and I still haven't shown you how to do that. It's very simple, but let's leave it till the next presentation. So a lower critical and upper critical value is found, let's say, these values. But in the normal, normally, while calculating for problems, at this step, we find the lower critical and upper critical values by ourselves. Anyway, given that these values, note that this area is tail area is going to be A1, this area is going to be A2. So A1 plus A2 is going to be 2A1, which is going to be equal to alpha, which I talked about. This is going to be type 1 error probability. All right, now alpha is going to be equal to probability that x bar is going to be smaller than 2.6 and x bar is greater than 3.4. Because in these conditions, we would reject the null hypothesis, but although this is actually the null hypothesis distribution, so there is alpha probability of obtaining any sample smaller than sample mean of 2.6 and greater than 3.4. So alpha is those two probabilities. So what we do is we just simply, since we know the distribution x bar here, we standardize this value. So 2.6 minus 3.0 over 2. We use these distribution values to determine the probability here for this term and to determine the probability here for this term. Note that since this is symmetric distribution, both of the probabilities are identical. Therefore, we simply write, since this result is going to be equal to minus 2.0, it doesn't matter. This one is going to be minus 2.0. We just find this probability and multiply by 2. So it is cumulative distribution function at minus 2 times 2, and this result is going to be 0.0455. And this is going to be our type 1 error probability. So when we construct the critical region with a lower critical value equal to 2.6 and a higher critical value of 3.4 for this specific example, which uses a sample of 16 observations, we are going to be committing a type 1 error probability of 0.05. What does that mean? Out of one, of course, not exactly 100, but think about the frequency interpretation. When we apply this random sampling an infinite number of times, about 95 or 94 point, I'm sorry, 95.5 of these samples, we are going to have an X-bar value within those two limits. But in 4.6% of these samples, we are going to have an X-bar value in this range or in this range. And we are going, in those cases, we are going to be erroneously rejecting the null hypothesis. So this is actually what I try to say here. And therefore, of course, 4.6% of the hypothesis test, the conclusions will be incorrect. Now I would like to talk about briefly about type 2 probability, which is denoted with B, and it's going to be equal to 1 minus power, and I'm going to try to explain what power is. All right, let's continue with the previous question. And now assume that X is the, and remember the original distribution at the mean of 3.0, but actually X is equal to now 3 points is normal distributed about 3.6 with the same variance. But actually we do not know that. Again, in reality, we would not be knowing this, but we just do this to analyze what's going to analyze the mechanics of the hypothesis testing. So assume that X is really distributed in this fashion. But as I said, we don't know it. So the null hypothesis, again, mu is equal to 3.0, and then the alternative is mu is not equal to 3.0. And since X is essentially normal distributed about 3.6, X bar, the sample that we are going to be collecting from that population, is going to be about normal distributed about 3.6, and the corresponding variance is going to be 0.8 squared divided by 60. And then X bar is going to have the corresponding distribution. Note that now the distribution of X bar is going to be about 3.6. So the actual distribution of X bar will have this form. Remember, in the previous case, when we assumed that, I am very sorry, all right, here, when we assumed that X is around distributed around a population mean of 3, right? It was here. Now it's going to be the population mean is essentially is equal to 3.5. So it's going to have this distribution here. The real distribution is this one. So let me go back to the next slide again. All right. I'm sorry, not 3.5, 3.6. However, note that we are still going to be using the same critical values. And those critical values are 2.6 and 3.4. This might seem a little bit confusing because usually it's a little difficult to visualize or to comprehend which of these are the things that we know and which of the things that we assume. So here the idea is something like that. Assume that there are two people here and one of them knows the ultimate truth or the truth about the population. But let's say your friend knows it, but you don't know it. So what you do is, or what I do is, let me speak with my friend. I construct a hypothesis, right? And this is my hypothesis, and I determine the lower and upper critical values. And then I'm going to take a sample from a population of unknown, from my perspective, mu. However, now your friend knows that this population is actually normal distributed with 3.6 population mean and the corresponding variance value. Hence, your friend is actually, without showing me, is actually actually drawing the probability density function for the sample mean. So this is in essence the corresponding, the sample mean that I'm going to be obtaining from the sample is distribution function. However, I'm going to be using these critical values, and I'm going to say that if the critical, if the X bar value falls in this range, I'm going to say that I'm not going to be rejecting the null hypothesis. If the X bar value falls here or here, then I'm going to say that, okay, mu is not equal to 3. But here is the point. Still, there is a possibility that X bar value could be in this region. Why? There is actually a significant proportion of, or significant area behind this probability distribution between 3.4 to 0 here. So that is going to be the type 2 probability. This area is the problematic region, right? So the area between 3.4 to 2.6, which is my acceptance region, is actually a very plausible probability for the real distribution. Therefore, what I call as type 2 probability is going to be equal to that area. And what's that? Excuse me, what's that area equal to? It's going to be X bar value from this distribution to come up come up a value between 2.6 and 3.4. And in order to find this probability, it's again very simple. I changed them. Z values, and then the Z value is going to be between -5 and -1, right? And it's pretty much obvious because this, when you standardize this mean value is going to be equal to 0. So this is going to be -1 to -5. And when you find these values, that -1 actually being smaller than -5 is almost as a 0 probability. So this is going to be approximately equal to cumulative distribution function evaluated at -1, which is going to be equal to 0.16. So we have a 16% or 0.16 probability of type 2 error. And what's that error? If, on the other hand, there is an important difference between type 1 and type 2 error. Type 1 error does not depend on the real probability. It depends on the assumed probability. Type 2 error, on the other hand, depends on the real mean value. I'm very sorry. Let me rephrase that again. Type 2 error depends on the actual probability distribution. Here is given as 3.6. On the other hand, type 1 probability does not care about this one, type 1 probability, because since it is based on the assumed probability distribution, and assumed probability distribution is the one that is in the null hypothesis here. So it does not depend on the actual probability distribution of the random variable. That makes it easier to calculate type 1 probability, because for type 1 probability, you don't need to know the real distribution of X bar. But here, note that if X bar were equal to, were distributed, normal distributed around 3.2 with the same variance, but but at a different population mean value, then this beta value here would have changed, because then the distribution would be around 3.2 mean here. So we would have this distribution, normal distribution here, right? Then we would be trying to find this area between this point and this point, this region here. So the beta type 2 probability depends on the shift of the distribution from the hypothesized one. That's a very important point. And power is simply 1 minus beta value. So power of this test is going to be equal to 1 minus 0.154, and it's going to be equal to, for instance, this one is a power of about 84%. And power here corresponds to detecting a shift in population parameter. As you can see, so a shift, if there is a shift from 3.0 to 3.6, right? Then this, for a shift of 0.6 units, I may say, usually it's not given in this manner, but it's given as a ratio to the standard deviation, but we are not going to go that much into type 2 error probability, so that's enough. So the power of this test for a shift of 0.8 units in population mean is about 85%. Actually, to satisfy your curiosity, let me give you a hint. Usually the sample size, because we are going to need a sample to do this test, and the sample size will be determined. Well, you cannot use any arbitrary sample size. Of course, increasing the sample size to high numbers will make all these calculations more reliable. But in real life, as I said previously, increasing the sample size too much may be costly. It may cost too much if you take too many observations here, too many specimens, and it may take a long time to measure all of these specimens. So you have to be careful about that sample size. It cannot be too large, but if it's too small, then the statistics will not be that reliable. So anyway, that sample size is usually determined by some power calculations, which I'm not going to go into. So if acceptance region is widened, alpha is decreased, but beta is increased. Now that relation is the main reason why I also talked about type 2 error. What do I mean by that? One may tend to think that at first sight, for instance, let's go back to the previous slide again. All right, here to lower the type 1 error, remember what was the type 1 error? It's actually those tail areas. So we just determine a critical region, and if it's inside this critical region, we say that's okay. If it's outside the critical region, we reject the null hypothesis, but it's incorrectly rejected. That was basically what type 1 error is. So one thing that you may naively do is you just increase these limits, put it here, and this one here. And this one is going to be, let's say, around 0. Or let's say 1.2, whatever, and this is going to be the symmetric of this one. So it's going to be 4.8, let's say. Assume that. So in this case, the area here on the left-hand side, here and the area on the right-hand side here is going to be very much smaller. And in this case, we really have decreased the alpha value, type 1 error probability. That's great, which is actually seems to be a very nice thing at first sight. But let's see whether it's a very, very good thing. In this case, what we do is we have note that this 2.4 or 2.6, this has been shifted to 1 point. I think it was 4, I cannot remember. And this has been shifted to 4.6, I guess. So therefore, this is our critical region. Critical point. So this is the critical region. Where is my, it's very difficult to, all right. And this is the acceptance region. Now here is the problem. Note that the bulk part of distribution is in acceptance region, which means if the mean of the population has really shifted from 3.0 to 3.6, samples from this population, their X-bar values will be most likely be in the acceptance region. Hence, we wouldn't be able to reject the null hypothesis. Therefore, type 2 error probability beta increase. So, moral of the story, if you increase the critical region, if you increase the acceptance region, alpha will decrease, but beta will increase. If you do the opposite, okay, I'm going to decrease the beta, you may say, then you decrease the critical region, acceptance region, I'm sorry, okay, then beta will increase, but then beta will decrease, but alpha will increase. So therefore, there is an inverse proportional relation between those two, which makes the tests, not only hypothesis testing, but tests related with treatments, medicines, diseases, also a difficult science, I may say. If you would like to for instance, detect all people who have that disease, right? And then you are likely to increase the probability of incorrectly assigning people who have not that disease as also positive results. I hope the idea is clear. So think about like this. If for every patient who comes, if you tell that, okay, you have that disease, right? Then note that your type 2 error probability is going to be 0. You are going to be detecting all the people who have the disease. But unfortunately, you are going to be detecting none of the people who have not that disease. This is going to be a problem. And if you can do the opposite for everybody who comes in, as a doctor, you may say that you don't have the disease, right? And in this case, there's going to be an alpha type 1 error probability of 0, right? But you are not going to be able to detect anybody who has that disease. So there's going to be, your beta value is going to be equal to 1. Your power of that test is going to be 0. So there's a trade-off between those two. Now comes the topic of how to calculate the lower and upper critical values. Well, actually, it's going to be the first part of this section. The second part is going to be an alternative method. Instead of finding the upper and lower critical values, an alternative method to conduct the hypothesis test. Actually, with this section, the conducting a hypothesis test concept will be totally covered. Then I'm going to continue with solving examples and talking about distributions and those things again. So how do we find the upper and lower critical values? The first method is called, the method to determine those values is called fixed significance level approach. So here is the idea. At the very beginning, we should determine an alpha value, which is going to be the significance level actually, and it's going to be equal to 1 minus confidence level as I told previously. Then we are going to be using this alpha value to determine the lower critical and upper critical values. It's going to be very simple. Let's continue from the previous question. And again, assume that X is normal and sigma is given as 0.8 kilomoles per meter cube. We decide we are going to conduct the following hypothesis test at given significance level 0.05. And as I said earlier, 0.05 is a very traditional value, I may say, used for significance level. Then again, this hypothesis test mu is equal to 3.0 or not equal to 3.0. Now, if H is true, then X is going to be normal distributed with mu 0 value, which is actually equal to 3, and the given sigma value. And now the interesting point, not very much interesting, we have covered this a couple of times before, but when we obtain an X bar value from a sample, if X is really distributed in this fashion, then the standard normal distribution, distributed Z, can be defined as X bar minus this given mu 0 value, which is the value here, the hypothesized value in the null hypothesis, minus mu 0 divided by the standard deviation square root of n. Which is, why do we have that? Because we are dealing with the sampling distribution of X bar, and this is going to be normal distributed with 0 mean and 1 standard deviation, which is actually going to be this curve that we have covered previously. Now, here is the point. We are going to define a lower critical value and upper critical value here. We can do it on the original distribution on X bar, non-standardized form. Actually, in questions, we are going to do that, but let's do it here on this standardized form. So here is going to be a lower critical value and upper critical value. But the question is, where will these lower and upper critical values stand, or where are they going to be located? Since alpha is specified, actually these are already located, but it needs only a couple of computations. So here is the thing. This part will be, since alpha is specified and since this is symmetric distribution, this area is going to be equal to alpha over 2, and this area on the right hand tail is going to be also equal to alpha over 2. So we need to find lower and upper critical values such that alpha values, or A1 and A2 values, and the summation of these values is satisfied with this condition, because it is this value which is given. Therefore, the left-hand side area is going to be 0.025, and the right-hand side area is going to be equal to 0.025. All right, so what do we do here? This value is going to be simply equal to minus z alpha over 2. Recall this notation from the previous chapter. Alpha over 2, or whatever that we write here, actually corresponds, if I use this term, it's going to be easier to understand. Whatever that we write here signifies the probability or the area here. So from this point to infinity. And since this is symmetric distribution, this point will be just the negative of that value. So z alpha over 2 corresponds to the point where actually on the right hand side you have a probability here, or area under the curve, which is equal to alpha over 2. So what you only need to do is to determine the z 0.025 value from the appendix of your textbook. And when you do that, you find the point to be equal to 1.96. Therefore, when this value is equal to 1.96, under standard normal distribution, this right-hand tail will be equal to 0.0025. And note that this is equal to 1 minus, actually it's going to go to infinity, it's going to be 1 minus cumulative distribution function of 1.96. This is going to be equal to 0.025. All right, so the acceptance region is going to be, let me get rid of all of these, between these two values, which are found to be equal to 1.96 and 1 minus 1.96. Note that at this point, you can easily convert them to the original variable, x bar. How? By multiplying by these values. Actually, if you multiply by sigma square root of n and sigma square root of n, right? You can obtain the lower and upper limiting values, the critical values for the original x or x bar here, without standardizing by the standard deviation. But we can also use this form. So anyway, now the limits are found. The next thing that we do is we are going to sample, let's say we are going to take 16 observations in our sample, and it's going to be consist of 16 randomly sampled observations. We are going to be finding the x bar value here. And let's say that x bar value has come out to be equal to 3.5. Now here's the point, if you just compare 3.5 to 3, okay, there is a difference. But for any sample, there's going to be a difference. The question here is that whether this difference in x bar, is it significantly different from the suggested or hypothesized value, such that we are going to suspect that mu has really changed, or whether this difference between those two, is it due to sampling fluctuations alone? This is the philosophy of the whole thing. So actually 3.5, where does 3.5 fall in terms of standard normal variables? 3.5 minus 3 over 2.2. This is the that 0.2 is 0.8. Note that divided by 0.16, because these are some number of observations here, right? So it's going to be equal to 0.2 in the denominator. So it's going to be 2.50 here. 2.50 here is this value, 2.50. Now, as you can see, 2.50 is not in the acceptance region. So since it does not lie in the acceptance region, but in the critical region, z value is here, as you can see, then we are going to reject the null hypothesis here. And we are going to say that there is sufficient evidence to suggest that the population mean of the mean of the new population is not equal to 3.0 kilomoles per meter. That is going to be the formal conclusion of this hypothesis test. They substantially suggest that population mean is not equal to 3.0 kilomoles per meter. So that is one way to formally conduct an hypothesis test. In the next lecture, I'm going to show that this approach is gives a totally identical result to the approach that we have used in confidence intervals. But be patient about that. Okay, now there is another method a brother of or a sister of this method that is being also pretty much used for conducting hypothesis tests. And in that approach, we do not determine these fixed lower and upper critical values. So here the philosophy is again this. Let's look from a bird's eye point of view what we have done. There's a suggested mu value. We construct a lower and upper critical value region. Then we take a sample, and from that sample we find an X bar value, right? Then using this X bar value, we see whether that X bar value, and it's normalized, standardized form actually, does it fall here within this acceptance region or this critical region. If it falls inside the acceptance region, although X bar is going to be different for mu value, for instance, if X bar were equal to 3.2, when we do this, it's going to be 3.2 minus 3 over 0.2. The result is going to be equal to 1.0. It's going to be here. Note that although 3.2 is different from mu, we would not be able to reject the null hypothesis. Why? Because that variation, that the difference between X bar and mu would be assigned to or would be explained by the sampling variance only. From sample to sample, due to the variance of the population and its reflection on sample mean, which is represented by standard deviation divided by square root of n, X bar values will change from sample to sample, and it's a very naive hope that it's going to be exactly equal to 3.0. There's going to be, of course, a variation, but is that variation significant such that we just lose hope of this null hypothesis and this distribution? If X bar is very equal to 3.2, we would not lose that hope, and we would say that we are not able to reject the null hypothesis. There is insufficient evidence to suggest that mu is not equal to 3.0. But X bar has come out to be a greater value, 3.5, which is not within those values. Therefore, he said this following: the substantially suggested population mean is not equal to 3.0. Okay. Now the p-value approach is, as I said, the lower and upper confidence critical values are not specified. And alpha is, by the way, also not specified. We just forget about those critical values. So you may ask, what using which criteria are we going to conduct the test? Let's see. There is something called that we are going to be using p-value here. So the conclusion of this type of conducting hypothesis test, again, the same hypothesis will be written using that we have used for fixed significance level approach. The same hypothesis says the same sample is going to be taken, the same X bar value is going to be used. The only difference is we are not going to compare this X bar or a standardized form of this X bar to some whether they lie within some critical values or not. We just skip that part. Instead of that, we determine something called p-value. Let's see what this is. All right, so the very same hypothesis test. Again, if H0 is true, you note that in hypothesis test, in these approaches, we assume that this is true. And under this condition, we determine this statistic. The very same thing here. Now we are going to determine X bar value using a sample, again, a sample of observation. X bar has come out to be 3.5. The very same story up to this point, except we don't have any alpha value, we don't have lower and upper values. Then we put this value again here, and we compute Z0 value as 2.50. It is here. Everything is the same, except we don't have these critical values, these boundaries, these acceptance and critical region. So Z is equal to 2.5. So how can we come up with a conclusion here? And this is where the p-value approach, the concept of p-value comes into play. The definition of p-value is a bit tricky to understand, So let me go first about very simple arithmetic, then I'll try to explain more in terms of intuition what it may mean. Okay, the idea is very simple. We find or we call the right-hand side area, however, of the observed value. We don't have anything to do with those critical values because we don't have any alpha value here. Nothing to do. It's just this area here on the tail. So this area 1 is going to depend on this observed value here. Note that in the previous case, the right-hand side and left-hand side area actually determined the value of z, but those areas were related only to alpha. Here there is no alpha. Z0, where the observed value determines this A1 value. So for this case, A1 can be easily found as this is going to be equal to 1 minus cumulative distribution function evaluated at 2.5. This is going to be equal to 0.062. Then here is the thing, the important point here. If you take the symmetric value of this Z0, it would be minus 2.5, and we would have this tail area here. You probably said, why do we take something like the symmetric or the negative of Z value? I'll come to that in a minute. I'll try to explain during the interpretation of P value. Let's only deal with the arithmetics right now. It's going to be A2, and this tail area is going to be equal to A1. So what we do is, what we call as P value is A1 plus A2. And since they are equal to each other, this is going to be simply equal to 2 times A1, which is going to be 0.124. This is what we call a P value. First of all, what is this? What is its unit? It is a probability. So as you can see, this is around 1.2, let's say 2% of probability. It's a low probability, but it's the probability of what, you may say. So here is the definition. It is the probability that this test statistic, which for this case, X bar, will take on a value that is at least as extreme as the observed value of the test statistic when A0 is true. In English, actually, it's already in English, but it may be complicated. The idea is, given that this population holds, this is true. In this population, from this population, we assume that we have observed such a value for X bar. What is the probability of obtaining an X bar value from this population at least as extreme as this one? When I say at least as extreme as, I mean any X bar value greater than 3.5 and including 3.5. That's why we include this right-hand side here. So the value that we have obtained, any other extreme value could have also been obtained. But what is the probability of that? Now, at this point, you may ask, what about this part? But note that extremeness has no sign here. Extreme means a distance from the origin or distance from the location. It may be both in positive direction and negative direction. So here, extremeness is defined as distance from this 3.0. So it could have been also equal to this X bar could have been also equal to 2.5 here. That wouldn't change anything in terms of being extreme. And in this case, we would include values smaller than 2.5 and equal to 0.5. So extremeness in terms of the negative direction would be X bar smaller than 2.5. So X bar greater than 3.5 and X bar smaller than 2.5 completes the extremeness definition. So basically, if you read this again, P value, this 1.2% probability, is the probability that X bar will take a value as extreme as 3.5 from this distribution. So 1.2% is a low probability, which means actually if we sample from this population, of course, again, from a frequency point of view, not exact, 100 different samples, only about one of them is going to have an XBAR value as extreme as this one. And when I say as extreme as, I mean it's going to be at least 3.5 from 3 or at most 2.5. So not between 2.5 and 3.5, there is going to be a single observation. Of course, this is actually as number of samples go to infinity, but the ratio is going to be 1%. So that 1% probability shows us or makes us think that it is highly unlikely that this assumption is invalid. So if we have a low p-value here at the end of the computations, we say that this is not due to luck that we have obtained this value. We do not assign luck to the outcome, but we assign that this assumption were incorrect. So the assumption came from the true, that the H0 being true is where this assumption came from. Therefore, H0 is true, is being rejected. Therefore, the more probable or the more likely result here, conclusion will be mu0 is not equal to 3.0. Now you may ask, what is the p-value for which we come up with the result that H0 is going to be rejected? Note that that p-value can be exactly made equal to the alpha value. So if this p-value were equal to exactly here 0.0, what was the value that we have found in the previous example? Let's see what was the value that we have used. 0.05, yeah. Let me get rid of all of these. So if, for instance, this value were, this p-value were found to be equal to 0.05, that would mean that we are actually exactly here at 1.96 in the critical region. Because if you think about how we computed the critical values, we said that this area plus this area is equal to alpha. So when your Z value is exactly on these on any of these critical values, P value will be identical to the alpha value. And since alpha value is usually taken to be equal to 0.05, any p-value smaller than 0.05 is usually deemed to be significant, therefore is usually an indicator that H0 is rejected. Any p-value greater than 0.05 shows that your Z0 value is within those limits determined by the significance, fixed significance level. So it is, we cannot reject H0. So that's one way to combine the p-value approach with the first thing, with the fixed significance level approach I talked about in the just the previous slide. But that p-value approach, unlike the other one, does not always gives you or does not need to give you a binary result, whether H0 is rejected or not. You may just report this p-value, right? And then let the person who analyzes this data or who reads this report come up with his or her conclusion. So when you, but the meaning of p-value, as I said, is important. 0.01 corresponds to that, the statistic that we have assumed, which we have assumed to come from the null hypothesis for the distribution, can only occur with 1.24% of the samples. So in other words, as I said here in the very last statement, the relation between p-value and alpha, p-value is the smallest level of significance, smallest level of alpha value that would lead to rejection of H0. So in other words, if you, for this previous, the same question but using the previous approach, if alpha is equal to 0.0100, was it 124? I forgot 124. If this value for significance level were used instead of this one, then the lower and upper critical values will be exactly here and here, and the lower critical value and Z0 value will overlap with each other. At this, when they are exactly overlap, of course, we are talking about continuous random variables. So the probability of continuous random variables being equal to each other actually 0, but since due to rounding off, we seem to discretize them. So any value I may say, just slightly smaller than this one, 0.0123, using this one would take the upper critical value here and would include the Z0 value. So in this case, we would not be able to reject this hypothesis. However, if you had made this equal to 125, then the upper critical value would lie just on the left of this observation here, and we would barely reject the null hypothesis. That's why it says here at this point here, p-value is the smallest level of significance that would lead to rejection of A0. If you make significance smaller than p-value, then you would not be able to reject the null hypothesis. So in the next lecture, I'm going to be talking about more numerical examples, and actually I'll talk about the cases where for distributions we do not know the sigma value, and also I'm going to be talking for the case where we need to conduct hypothesis tests also on population variances and things like that.